Well, welcome everyone. Welcome to for coming in the in-between week, as it were. The opportunity arose because Rick was keen to come and talk to members of the Edinburgh Geological Society, but from, as you can see, Virginia Tech, travel options are a little bit more constraining than for some of our speakers. And so this, Richard, I think is your midterm break, semester break. So I'm very pleased. I think we should all recognize the effort that Rick has gone to come over to fit Edinburgh GeoSoc into his UK travel plans on this occasion. He's not a stranger to these parts by any means, but he has taken the time to come up and speak to Edinburgh GeoSoc, in part because we have some connection with Rick and his students and supporting them in their endeavours. And we'll hear a little bit of that tonight. This also continues the theme that we've been pursuing, which is why I was keen to find space for Rick, as it were, in our pursuit of chapters in the forthcoming Geology of Scotland. There's no update from last week. It's still June, as far as I can tell. But I was pleased in Tony's talk last week to see a front cover in one of his slides. So they've obviously made quite a bit of progress along the way. So it is coming. Rick is very much the lead author for the Scandian deformation, that sort of Silurian into Devonian deformation that is perhaps best recorded in the Northern Highlands as opposed to the Grampian Highlands. But I think, as Rick is going to demonstrate to us tonight, it's not quite so simple as that. So when was geology ever simple? So really, without further ado, Rick is coming to us from a point of view of many years of experience working in this ground, supervised by people like Tony Barber, who had a big track record in this area, as in the Northern Highlands as well, and latterly has devoted a lot of his research efforts to this part of the world. Hence, he's the lead author in Chapter 8 and trying to pull together a diverse group of protagonists, I guess we should say. The Northern Highland terrane, an overview from Rick Law and his colleagues. Good luck.
Being better? Yes. Okay, good. Right. So as Graham mentioned, my purpose tonight is to give at least a flavor of some of the new material that's gone into Chapter 8 for the new 5th edition of Geology of Scotland. We'll be concentrating tonight exclusively on the Northern Highland terrane. So that's between the Great Glen in the south and east and the Moine thrust zone in the north and west. So basically within the Moine supergroup of rocks. Sorry, I shouldn't have said that, Martin, should I? No, okay. Sorry, old habits die hard. And I'm going to look at particularly some of the work that my students have done, but also collaborating, certainly with Martin several times in projects. We've been doing in the Northern Highland terrane for the last 15, 20 years, I suppose now. So I'll take a few selected highlights from that work to illustrate some of the new results that have come out the last 10 or 15 years, I suppose, really, on the structure, the metamorphism, and the isotopic dating side of Chapter 8. Matthew Thirlwall has already covered the igneous side of things for Chapter 8, I think about 3 or 4 weeks ago, something like that. Okay, so let's get started. And the talk will probably have 2 parts this evening. We're going to look first at a transect from the Moine thrust across the east coast, this transect here, basically from just south of Ullapool at Loch Broom, through towards Ben Wyvis. So it's this traverse along here, the BB prime line, which is shown by this cross section we'll see later on again. It was actually drawn by Martin Cravenden from one of my students. Oh, blimey, 10 or 15 years ago. Long time now. So we'll look at that one first. We'll also look a little bit at what's known as the flat belt to the south, where literally the rocks are fairly flat lying as you approach the Great Glen Fault. So a little bit down here. And I particularly wanted to mention that because that's student work that's been done under funding from the Edinburgh Geological Society as well. So mention of that. And then probably the last part will be an update on the structure and particularly the metamorphism and isotopic dating of the Sutherland Moine rocks up in the north here, shown by this cross section. We'll look at in a bit more detail later on through here. And that will probably take us to a reasonable time for finishing up. If anybody is really a glutton for punishment afterwards, we can have a vote or however you do these things. There is a big update on work we've been doing on the Great Glen Fault over the last year or so, and particularly evidence from mid-crustal shearing on the Great Glen. But I'll leave Graham to make the decision on that when we get to that point. So let's start off with the first of our study areas from Dundonald in the west on the Moine Thrust through to Ben Wyvis, Garve on the east, and look and see what's been happening there over the last few years. It's very much a summary of a lot of what students have done at Virginia Tech, PhD students at the top, master students at the bottom. This evening, particularly for the Sutherland Moine in the north, I'll be particularly concentrating on work that my former student Calvin Mako has done. Calvin now is a geologist working for the Arizona Geological Survey. Temperatures of 115 to 120 in the summer. They only do field work in the winter. And going down through the generations, this former student here, Brandon Spencer, not a PhD student of mine, but a PhD student of the University of Kentucky, of my former PhD student, Brian Thigpen. So we're really starting to come through the generations a bit here. And then as well, I will say a little bit, as well as particularly Calvin and Brandon's work, I'll mention at least ongoing work by this student of mine at the moment, Ella Davis, who is partially being funded by Edinburgh Geological Society. So at least wrap a little bit of that in there. Okay, now let's start off with a map of the Northern Highland terrane. And here I've put in or compiled information on the linear grain-shaped fabrics that have been mapped in individual outcrops all the way from the north coast, coming down certainly towards Fort William. And just to get your eye in, the Moine Thrust is on the west here, coming down, Great Glen obviously there. Here's the Southern Moine, lots and lots of data. And if you follow the trend of those arrows that mark the direction in which the linear fabrics plunge in the rocks, you can see they start off nearly east-west, perpendicular to the strike of the Moine Thrust. And then as you trace them eastwards, they turn and come locally almost to a north-south trend. So they bend through nearly 90 degrees. Nothing new about that. That's been known since British Geological Survey mapped through the area over 100 years ago. But I want to look at what that lineation trend is telling us in terms of the direction in which the rocks have moved, the directions of transport parallel to that linear fabric there, okay? Because at the regional scale, not really much has been done since Frank Coles Phillips back in the 1930s. And his PhD student, Colin Crampton at Bristol in 1955. So it's many, many decades since anybody has taken a detailed look either at what you see in thin section in terms of microstructures that may give you shear senses to go with that transport, the temperatures at which that shearing has occurred, and the direction of transport of the thrust sheets themselves. Okay. Now, by convention, the foliation is not shown there, but the lineation on the foliation is usually referred to as a local D2 structure in there. Okay, now let's start off on that transect, but before we do, Graham asked me to put in a bit of information on the data that we use. Now, these rocks are all plastically deformed. So the quartz grains in them have been deformed at certainly over temperatures higher than 300–400 degrees. And as the crystal lattice inside those grains shears, the individual crystal directions take a new orientation due to the shearing within the crystal lattice. That's been dealt with experimentally for many decades. It's also been numerically modeled, and it's very useful because the pattern of crystal preferred orientation of the quartz grains in this case tell us a lot about the deformation. Now, here we have what's known as a quartz C-axis fabric. It is a stereographic projection, and this line here is the foliation, which is going from east-west and is vertical. The linear fabric is here and here shown by those green dots. The pole to the foliation is this line here. And this is a contoured plot of 1,000 grains measured. So you have 1,000 orientations of C-axes within that particular rock, but in a thin section, that have now been plotted on a stereonet in specimen coordinates relative to the foliation and the lineation. Now, that pattern of preferred orientation can tell us a lot about the 3D strain the rock has undergone, and also gives us information on shear sense. Some of you may have seen this very famous plot at the top here, known as a Flynn plot, invented by Derek Flynn, Shetland fame, back in the 1960s particularly. And it's a way of showing three-dimensional strains so that a pure flattening deformation, basically a pancake shortening, is along the base. So a cube will go to this shape. A plane strain, where you're shortening in one direction and stretching at right angles, but doing nothing in the third dimension, is shown by this diagram here. And what's referred to as a constrictional deformation, some people refer to it as a toothpaste deformation, is where you're pulling out and simultaneously shortening in all directions at right angles to your pull direction. A bit like literally squeezing a tube of toothpaste. Now, the important point for us is that the type of crystal fabric that develops is diagnostic of the 3D strain. So where we see this type of fabric here, often shown as a two-girdle fabric, one girdle, two girdles, that's diagnostic of approximately plane strain deformation. So that corresponds to this here. But you can take it a lot further than that. You can start to look at asymmetric relationships between this crystal preferred orientation here and the sample coordinates, particularly in terms of, say, the pole to that foliation there. And for a top to the left shear sense, as shown on that diagram there, then this angle here between what's known as the leading edge of the fabric and the pole to foliation should be smaller than this trailing edge angle here, okay? So we can measure that when we analyze individual rocks, and we can look for potential shear sense indicators. Not only that, we know both from numerical simulation and experiments that this cross-girdle fabric crosses the foliation at right angles to the maximum principal stretch direction, the direction in which the rocks are principally stretching. So we have built in, when we do these analyses, a test of whether these lineations that we measure across the Scottish Highlands are just, say, an intersection lineation between two pre-existing fabrics, or really do represent the principal stretch direction in which that rock has been deformed, and hence the direction in which the thrust naps are traveling. That's important, okay? So here is one example. This example is the same as that one there, and that was taken about 3 miles south of Ullapool on the side of the road, where the Moine thrust crosses the road just south of Ullapool, and you have mylonites sitting directly on top of the Moine thrust, literally on the roadside by one of the drainage culverts. That sample is this one here, and comes just from here on the south side of Ullapool there. The point is, when we have that information, and it's always measured on sections cut at right angles to foliation, this section here, and parallel to the mineral lineation, so all the data will be shown in these cross sections here, we can immediately work out the shear sense associated with that plastic deformation. Okay, so let's go to our first area. And this is largely work that I published with Martin 2 years ago, 3 years ago now, Martin, something like that. And it's going to be a transect through from just south of Ullapool at Loch Broom in Dundonald, through basically following the main road through to the Garve Benwivis area, shown in more detail, just an enlargement on the right-hand side here. And we've got 3 overlapping areas. We'll look in first at some detail at this area here, and then we'll at least summarize what's happening in these 2 areas, basically transecting right across the Scandian origin from coast to coast here, okay? But notice that the lineations change in trend enormously. They're basically east-west at the Moine thrust, and they turn through nearly 90 degrees until they're going nearly north-south. What's that telling us about the directions in which the rocks have moved during this deformation? Okay, so on the right there, a detailed map of our sampling locations. Loch Broom here. This is the main road that you take from Inverness up to Ullapool there. So we've got a series of rocks collected, some along the Moine thrust itself, and then in a detailed traverse coming through like this to those who know it, Braymore Junction in here. So a series of rocks, probably more meaningfully shown in terms of the locations on this British Geological Survey cross-section for the, it's not the Ullapool sheet, is this one, Martin? Or is this the Fanix? You drew it. Oh, okay. Yep, okay. Anyway, the point is the Moine thrust here is dipping at about 15, 18 degrees towards the east. And samples obviously collected here at outcrop. And so we can log the distance of these individual samples above the Moine thrust. So as we go eastwards, we're getting a transect higher and higher and higher above the Moine thrust until we come to this first major fold here. In that traverse, the lineation trend changes by 90 degrees. And on the diagram above, we have horizontal distance parallel to the cross section versus lineation trend, 080, 090 due east, 120, 140, 160, 180, etc., etc. So you can see as we get higher and higher above the Moine thrust on the base there, that lineation is swinging around over nearly 90 degrees, okay? That potentially is telling us our transport direction is swinging through 90 degrees, all within a zone of absolutely planar mylonite, crystal plastically deformed rock. There are basically no folds in this transect at all until we get to these major folds further in. Now, just to give you the data, here is the actual data in terms of those crystal fabrics. Basically, all that is telling you is they're very, very similar, like this, that first one that we got. You can measure the angles, that C1, C2 angle between the pole defoliation, leading edge, trailing edge, to get a potential shear sense. They're all top to the left shear sense as we look at all these fabrics. Here plotted on that C1 versus C2 angle, the only thing that matters is if they fall in this gray area here, where the C2 angle is greater than the C1 angle, then all those fabrics are consistent with a top to the north through to top to the west sense of transport and motion. I tried to summarize it in this sort of cartoon here at 3 levels above the Moine thrust plane. Close to the Moine thrust plane, basically the lineations are going east-west, and the sense of shear is top to the west shearing. Utterly nothing new about that. That's been known for over 100, 120 years or so, but just confirming that the Moine thrust mylonites directly above the thrust plane are associated with top to the west thrusting going over the foreland. But as we trace those lineations structurally upwards, we find the lineation comes round to a more northerly trend, and there the sense of motion is top to the north. So top to the north motion, it's structurally high levels, and then as you trace down through that platy zone of mylonites, you gradually transition from the top to the north motion through to a top to the famous west motion on the Moine thrust. And in looking at nearly 30 samples here, I only found one exception to that rule, and that happens to be a quartz vein that I suspect is sandwiched between 2 blocks of rock moving independently on either side of the quartz vein. So it's a very consistent story with structural distance. We're changing as we go down through the sequence of mylonites from top to the north motion. Certainly wouldn't expect that on the Moine thrust, but it's there. And as you go down, things swing through 90 degrees until you're in the classic top to the west motion. Now, in that zone, all the mylonites are perfectly planar, so you can't explain that change in trend by, say, later folding, because the foliation on which they lie is absolutely planar and parallel to the underlying Moine thrust. So something certainly is changing enormously over that structural distance of about 4 kilometers above the Moine thrust plane. So changing from top to the north, gradually turning as you go deeper to top to the west motion. Okay, so that's what I'm really trying to summarize here. Seen these diagrams before, and we're literally going from top to the north motion when we're at this sort of structural level and transitioning to top to the west motion when we get close to the Moine thrust. Now here, all that 90-degree swing in lineation trend all occurs within just the lowermost part of the Moine thrust sheet. So it all occurs in the lower part of the Moine thrust sheet, the lowermost 4 kilometers, whereas if you look at that lineation trend change up in Sutherland towards the north coast, it's at a totally different scale. That trend is now occurring, not just like a hairpin bend in there, but is occurring much more gradually over the Moine thrust sheet, the Benmore thrust sheet, and into the Naver and the Skinsdale thrust sheets, nearly going from west to east coast. So it's at a totally different scale in the north to what we see in the south here, okay? And I think personally that the Northern Highland terrane in the far north of Sutherland is very much a different beast to what we see down in, say, the Ullapool through to Ben Wyvis area. Very different, as perhaps we'll see as we go on, both in terms of isotopic dating and in terms of structure. So let's come now to the more southeast part of our transect, what I've called for the paper, areas 1 and sorry, areas 2 and 3 together. And this is Martin's cross-section that he drew through. We've looked in detail at this part here, the planar zone. There are a series of kilometer scale West Virgin folds, and those West Virgin folds fold or deform this early planar fabric that we've been dealing with. So these are later folds that are folding that fabric that we've been looking at. However, we're very lucky here because detailed mapping by Graham, by Martin, et cetera, for the remapping of the Moine thrust shows very nicely that these fold hinges that are at the kilometer scale are basically parallel to this now north-south trending subhorizontal lineation. That's very useful because it means, because the fold hinges themselves are parallel to that earlier lineation, the lineation remains in its original orientation. It's not being deformed into different orientations. The rocks are actually folding around that lineation. So when we look at this area in here, let's look now at samples going through here, through this folded terrain. I won't do as much detail of the fabrics, but in detail, when we take individual samples around these kilometer scale folds, we find, just as we did further to the west, that all those fabrics are still associated with top to the north overthrusting, and it only gets complicated on the overturned limbs of some of these folds, where literally everything is flipped over and it appears to be going the other way, but that's just later folding, turning our reference frame over. If you correct for that, everything's back to top to the north motion. So the Moine thrust, I hate to sound like H.H. Reed, but is a very localized structure. And it really doesn't tell us very much about what's going on in the origin back to the east, which is the main core of the origin. And H.H. Reed put that very, very bluntly in the early 1950s, saying it would be much better for Highland geology if they ignored the Moine thrust for 20 years and concentrated on the interior of the origin. It's a great few paragraphs that he wrote there. And although I worked on the Moine thrust my first 10 years in Scotland, I think he's probably right. Anyway, okay, so that top to the north story keeps going back through this folded domain in here. It just locally complicates it, where it literally flips things over on the overturned limb there. So the zone atop to the north thrusting is actually much, much wider than the very narrow Moine thrust. Now, we are traversing through another of the major thrusts of the Northern Highlands, the Scorbeg thrust. It's been known of certainly since the late 60s, early 70s. It's a thrust zone within the high metamorphic grade core of the Northern Highland terrane. Very little is actually known on it in terms of the orientation of shearing on it. Very little is known on the sensor motion on this Scorbeg thrust. Well, here at the eastern end of our traverse, basically in the Garve Ben Wyvis area, at the eastern end of the traverse, we're actually traversing across the Scorbeg thrust here. All the fabrics that we looked at are consistent with top to the north motion on the Great Glen, on the Scorbeg thrust. So we're looking at this area in here now in detail. And here, what we've done is look at the recrystallized grain size of quartz in the hanging wall, in the footwall, and tracing to the actual mapped trace of the Scorbeg thrust here, which is what's on this diagram. So here we have a structural distance structurally above the Scorbeg thrust here, going upwards, and then structural distance below the Scorbeg thrust coming downwards. So we're going up to about 2.5 kilometers above in the hanging wall, and we're going down to about 1,500 meters below in the footwall. And as you can see here, there's a dramatic reduction in recrystallized grain size as we come down towards that mapped thrust contact there. And then in the football, it once again increases in grain size as we go away from it. That is very strong evidence that at least this segment of the Skirabake thrust was moving as a structure when this recrystallization was occurring. But more than that, recrystallization is what's producing those quartz fabrics that we've looked at, from which we got our shear sense, top to north motion. So at least on this segment of the Skirabake thrust, we can be fairly confident that motion did occur on the Skirabake thrust here, associated with that top to the north motion, and it's being concentrated on that mapped boundary there, okay? So that's looking now at that transect there. And we can, for example, restore that fold belt. Basically, take away the folds, stretch the rocks back to their original length before they were shortened by folding. When we do that, and I've done that here between where the folds first appear, near Braymore Junction, out to the Garve, Rogie Falls, Ben Wyvis area here, basically just flatten that out. So we end up with a tabular sheet of rock here. And originally, it was about 55 kilometers wide when we restore that folded panel there. And it's all associated with top to the north shearing, parallel to the present day Moine thrust zone. So we know that that was at least a 55-kilometer wide panel, all of north, top to the north thrusting. Now, this is where I come to thank Geological Society of Edinburgh for some student funding. I have at the moment a student, Ella Davis, who is working in the southern Moine. I'm not going to say much about her work tonight on more southerly transects of the Skirabake thrust, but I will say a little bit on her work on the Northern Highlands flat belt down here, where on this cross section, you can see the rocks are literally pretty well flat lying in here. There's no folds like in this steep belt further to the east. So she's been looking at the same sort of microstructures, crystal fabrics in this Highland flat belt here. And when we look at the data from there, after a while, we get used to looking at these things. So here we have about 8 samples from Cannock in the north, coming down from Fort Augustus towards Glengarry in here, all north-south, pretty well trending linear fabrics, and they are all associated, once again, with top to the north motion. So that means this area is in here, our previous cross-section stopped there, so our restored cross-section at this end here stopped about there, but we know that top to the north shearing continues to the south and east in present day coordinates through this flat belt in here. And that means that the original flat belt, if we also build in what we have here, we're restoring that section, the flat belt in here, the original width of the flat belt was actually at least 80 kilometers. So another 25 on top of what we had on the cross section there. So we know that that domain of top to north shearing was originally at least 80, probably at least 90 kilometers wide before it disappears under the younger Devonian sediments and ultimately gets cut off by the Great Glen fault as well. So it's not an insignificant little zone, a local curiosity. It's actually straddling quite a width of the whole of the Northern Highland terrane. Okay. Okay. So now, what's the age of that top to the north shearing? What's the age of the transition from top to the north to top to the west shearing? So to answer that, I've actually been allowed by Matthew Thirlwall to mention some of his isotopic work that hasn't been published yet. But let's start off, before we get to Matthew, back on this cross section here. And we're going to be looking at rubidium strontium dating of white mica. And those white micas are certainly growing during this shearing. No doubt about that whatsoever. The historically oldest date was collected here near Dundonald, near Loch Broom in Ullapool. And a date was published in here in 1998 by a group of geologists from Leeds, Freeman et al. And they dated by rubidium strontium, the white micas there. And they came up with an age range in the different Moine myelinite micas, ranging between 430 and 410. So that's sort of midish Silurian through early Devonian age, but about a 5-degree uncertainty. And they said that most of the ages were clustering at about 430 million years. So mid-Silurian age shearing. Now, an extra wrinkle is they used, obviously, the decay constant that was relevant at their time. In 2015, that decay constant was estimated by Igor Villa at the University of Milan, and it means that ages here are now known to be about 7 million years too young with the re-estimation of the correct decay constant. So we would now say that those micas along the base of the Moine thrust sheet here were crystallizing between about 437 and 417 million A, with most of them clustering about 437 million years. Now, for rubidium, strontium, and white mica, those ages are locked in when the minerals close or cool through about 530 degrees centigrade. Okay, that's useful because we know from other work we've done on these myelinites that most of them are lower amphibolite facies and crystallized in about the 550 to 600 degree range. That's very useful. So we're not dealing with cooling ages here. We're dealing with crystallization ages during the ongoing shearing. Very useful. In contrast, this blue one here is a traditional argon-argon cooling age, actually measured by Brandon Spencer, this second-generation PhD student of mine from the University of Kentucky. And those cooling ages are relevant to the mineral cooling through about 400 degrees C. So you would expect a younger argon-argon age because it sets in at a lower temperature. And so here now, Brandon has estimated very tight data coming actually from these grains. I actually gave him some sample from the rock that has these thin sections here of the white micas. They're cooling through 432 degrees, through 400 degrees at 432 million years. So between, say, about 437 and 432, the rocks have cooled through about 100 degrees or so, maybe 150 degrees. Now, coming further back into the pile, here's the first of Matthew's still unpublished ages. The samples were collected by Rob Strachan, but very nicely, they fell right on the transect I was doing. We didn't realize we were working on the same project until we were having a drink outside a pub in Ullapool. And I said, what I've been doing. He said, well, that's weird. I've been sampling the same outcrops for a different function. So we started putting things together a little bit between the two. Now, this one here by Matthew Thirlwell, this one here now is coming in at an age, rubidium strontium white mica age of 434 million years. So this rock here is cooling through about 550 degrees at about 434 million years. Let's go further eastwards. So now here's the whole of Martin's cross-section. And I've summarized now the changing rubidium strontium ages as we trace them eastwards, particularly into the main north-south shearing domain. So you can start to see a pattern. About mid-430s on the Moine thrust zone, coming through to here. By the time you get eastwards, going towards the high temperature core, but still on top of the north shearing, we're back at about 440 million years when it was cooling through about 550. When we get back to the Skerbeck thrust, 3 separate samples, 3 very different ages here, but certainly the younger one matching up with that one. But more importantly, here we have a totally independent age by Peter Kaywood, used to be at University of St Andrews on monazite age dating, and Peter here coming in with 454 million years for a crystallization of monazite there. So you can see the general trend that's coming in there. Mid 450s, back in the high temperature core, coming to 430s as we come out towards the foreland margin of the system and we transition from top to the north shearing to top to the west famous shearing on the Moine thrust zone there. Okay. Now, let's take our second area in the Moine of Sutherland in the north. Very different geometry. Here is a cross-section line from the Moine thrust going eastwards to the coast here. So here it is in more detail. And underneath, one of the cross-sections that we drew for chapter 8 in the new edition. So at a much, much bigger scale, so we're dealing down here, and we have a series of thrust sheets, all of those thrust sheets dipping eastwards like this. And as we'll see, as we traverse from the Moine thrust in the west into the high temperature core of the orogenic belt, we're steadily rising in temperature, both of metamorphism and deformation. Now, let's come back to those damned quartz fabrics, but for a different use. One of the uses that we've been talking about is certainly using those asymmetries for shear sense. But there's another use they can simultaneously be put to, and that's estimating the temperature of deformation. This is a calibration put forward in 2016 by a group of incredibly gifted young Brazilian geologists, taking field studies around the world where independently there was good evidence for temperatures, at least of metamorphism from classic metamorphic petrology, and an argument could be made that those minerals crystallized during deformation. And they were basically summarizing data from around the world. So this is real natural data sets. Here we have opening angle, 40, 60, 100 degrees. So that's that combined angle there versus temperature of metamorphism in the individual case studies. So you can see as you raise temperature of deformation, there's a steady climb in that opening angle. It actually, when you get to this temperature here, the reason that you have this kink is that very different crystallographic slip systems are activated when you get to this critical temperature here of about 650, 700 degrees. It also closely corresponds to the alpha-beta transition in quartz for anybody who's into mineralogy. That's not necessarily an accident. But the point is, we can measure that angle in the field, and we can then compare it with the likely temperature that would come from this calibration. So simultaneously, we can get shear sensors and hence transport directions, and we can also assess the temperature of deformation. Notice I said deformation, not metamorphism, which may or may not be the same thing. Okay, so let's have a look at that. Here is data published about in 2013 on a transect here from the Moine thrust south of Loch Eriboll, going through Altnahara and up onto the summit of Ben Cleabrick. So we're transgressing across the Moine thrust sheet, the Ben Hope thrust sheet, and into this Naver thrust sheet, which is in the high temperature core of the orogenic belt. Well, by this time, you've got used to seeing these fabrics. They're telling you they're plane strain. We can look at the detail of the asymmetry. And in all cases, just like that previous transect, these angles show a progressive transition, top to the west thrusting on the Moine thrust. Absolutely no surprise about that. And going over, but on a much, much bigger scale than that previous traverse here, to top towards the north, thrusting in this high temperature core, where we get up to temperatures, as we'll see, of the low 600 degrees. So let's compare the temperatures of deformation that we estimate from these with petrologically determined temperatures of metamorphism. Okay, so we're traversing through like this. Here is a compilation recently updated by Calvin Mako, now Arizona Survey. So this is now map distance horizontally. So this is map distance along that transect here, crossing through the Ben Hope thrust here and the Naver thrust there. And we have temperatures of deformation coming up vertically here and the opening angle next to it. Now, the temperatures estimated from those quartz fabrics are shown by these brown filled in circles. So you can see we're in the high 400s estimated at the top of the Moine thrust zone itself, climbing as we climb across the Moine thrust sheet up to mid 500s. And then as we cross the Ben Hope thrust sheet and into the Naver thrust sheet, coming up to the low to mid 600 degrees in terms of those brown circles all coming from the fabrics. Now, two other data sets here. In the triangles, classic metamorphic petrology, we have temperatures of metamorphism indicated by garnet biotite thermometry, an exchange of trace elements between garnet and adjacent biotite. So you can see there is certainly at least a mirroring of that trend that we see from the deformation fabrics with what we see in terms of the garnet biotite thermometry. That was stuff that was published in about 2013 by former students. A rather unusual one, monazite xenotime thermometry. Where you have monazite and xenotime next to each other, they exchange trace elements. And they exchange the trace elements at different degrees of efficiency depending on the temperature. And so if you do have monazite and xenotime next to each other, don't ask me for the details, I'm not a metamorphic petrologist, but you can estimate the temperature at which the adjacent monazite and xenotime crystallize, and we're exchanging trace elements. Monazite xenotime thermometry. And here in these square boxes, we have, some of them are in green, some of them are in gray. We have the temperatures for monazite xenotime thermometry. So you can see they're falling within the middle of that field that we have there. And as we get further back into the Naver thrust sheet, we're getting to very high temperatures here, high 600s, getting close to melting. They're becoming migmatites, literally. Then interestingly, we see a trail off like that, okay? Now, those monazites are really important because they're measured on a laser, in this case at Santa Barbara, and you can simultaneously measure uranium-lead concentrations in the grains. So you can isotopically date them, ultimately, and on the same grains, and even on the same parts of grains, core to rims, you can, if you have the monazite and xenotime next to each other, you can date the spots that's undergoing that isotopic exchange. You can simultaneously, on the same grains or even parts of grains, estimate an age of crystallization and a temperature of crystallization, known as LAICPS, laser ablation inductively coupled mass spectrometry. Wow, I did it. Okay, way beyond my ken, but the students lap it up, certainly. Okay, but it's very powerful because this is the first time you know you're dating a particular event, you're even on the same part of the grain. I know it's become passé. BGS has got lots of facilities, I'm sure, for doing such things. But very powerful because now for the first time we can directly date the deformation and get the temperature at the same time. So you can see the correspondence there between the data sets. Now, a little bit more about compiled geochronology. I've taken this pretty much direct from the new chapter 8 in the 5th edition. The top diagram here is a compilation that Calvin Mako made of all available isotopic dating of metasedimentary and meta-igneous rocks in the Moine of Sutherland. So there is no significance to that vertical scale. It's just showing where those different ages are, one after another. No significance to the vertical thing, but you can see most of those ages there are falling in between about, say, 420, 425, and the oldest ages, I'll deal with this separately, coming in at, say, about 430, 435 there. So in these northernmost Moine rocks, a lot of the previously published data, both from the metasedimentary rocks and in the igneous rocks, are all coming in about the 424, 425 to 433 MA. So mid-ish Silurian, classic Scandian ages, as Graham introduced it. Now, there are some outliers here, and these are largely outliers by a former student of Matthew Thirlwall and Rob Strachan by Anna Bird, hence the name B here, and I'll deal with these separately in a minute. These are clearly much older ages that I'll deal with separately. Then I'll look in more detail at these monazite and titanite ages, nearly all monazite, that Calvin collected from the Naver thrust sheet, that high-level, high-temperature thrust sheet. And remember here, we have the luxury of simultaneously, for the same parts of grains, estimating temperature of deformation and the time at which those grains crystallized. So here, and I'll deal with this in more detail in a minute, we have a temperature versus time plot. I'll deal with that in more detail in just a minute. Okay, let's look maybe in a bit more detail at these in just a second. So here are these outliers. This one here is actually Catherine Goodenough data from the Glendessery cyanide. But these Bs are all coming from garnet ages done by Anna Bird at Royal Holloway College, published in 2013. Here are the location of some of Anna's samples. And these are garnet ages using Lutetian, Hafnium, Sumerian, Neodymium. And as you can see, most of these are coming in at about 450 to 460 million years. So in these garnets, we seem to be getting a window into an earlier phase of deformation that's largely been overprinted and obliterated. It's a very, very strong Scandian overprint, picked out beautifully by this monazite data, but in these garnets that Anna analyzed, we seem to have a window, just a very, very occasional window into older events that have largely been overprinted and evidence totally destroyed. So there's something going on before, but we only get tiny peeks into what that earlier deformation may be. Okay, now let's think about those ages in a broader context. Let's say, for example, take the age of shearing on the Moine myelinite south of Ullapool. If you remember, certainly with the new rubidium-strontium decay constant, that came in at about 437, shown by the green arrow for location and the green arrow on that time scale there. So nearly all these ages here in the northern Moine are clearly much, much younger than the shearing on the Moine thrust in the south, much younger. If we take southern Assynt here, famous obviously for thrust geometries, famous also for alkaline magmatism. So we have, for example, the Borrelin intrusion, the Loch Ailsh intrusion, well, certainly work that Catherine did in conjunction with Graham and Martin, and isotopic dating of these intrusions at BGS, they very narrowly bracketed down through cross-cutting relationships with these alkaline intrusions that the Moine thrust was ongoing with myelinization at about 430 million years here on the Moine thrust itself in southern ascent, but had basically, in terms of ductile motion, ceased by about 429. That's pretty tight timing, to say the least. But the point is, those ages are older than most of what we're picking up in these more hinterland, higher temperature thrust sheets. We always tend to think that the deformation and metamorphism is progressing from hinterland to foreland, and so we'd expect the deformation and the metamorphism to get progressively younger, maybe. This is not happening. Those ages here are significantly older, with the exception of these windows we see with the garnets. Those ages are significantly older than what we're picking up in this high temperature core. And we'll start to deal with Kelvin's detailed monocyte data now in the high temperature core. So now we can start to see some of Kelvin's data in a bit more detail. Remember, very tight controls between age of crystallization and temperature deformation. So you can start to see here a prograde heating path getting to a maximum temperature here. That's actually a titanite one, but that's okay. And then going into cooling here, dropping down as they get a little bit younger. We got an extra bit of data that I'll bring in a minute that's just been published, but then you have to get those rocks to the surface by about 405 million years, because we know, as I'll detail in a minute, we have Devonian or Old Red Sandstone basins sitting on top of these crystalline rocks. So they had to obviously be brought right up to the surface, everything planed away, by the time these early Emsian lower Old Red Sandstones were laid down on top. So you can see how quickly we have to bring them down there, okay? But one of the things that comes out of this, there are much younger phases of metamorphism back in the hinterland than we see on the leading edge of the whole orogenic belt. Not what we were expecting. So let's look in a bit more detail at this set of monocyte data. You can see the general idea: cooler temperatures, older, going to maximum temperatures, and then starting to cool here. So we can look in a bit more detail at that data here with some of these plots. And in here, for example, here is a single grain where you can analyze parts of that one single grain and start to get both temperature and age of crystallization out of the different parts of the grain. And you can check in those ages against the core and rim zones, et cetera, et cetera. So you can see here is a core. And you can see we're coming in here now with an age of about 427, something like that. And you get towards a rim and an outer rim, and we've actually got a bit of constraint there from a different mineral, but you can see we're going from prograde, highest temperatures, to retrograde. And so we can look at it in this detail, and at least over this time interval from about 430 to about 420, 417, we can recognize a prograde heating path, an average of about 50 degrees C per million years. We can recognize peak temperatures, and we can see the start of cooling at about 20 degrees C per million year, okay? So peak conditions reached at about 424 plus or minus about 2 million years there, with initial heating and then initial cooling rates of about 15 and 15 degrees C per million years. Okay, now, oops, ooh, blimey. Oh, what happened? I have no idea. I think we're gonna have to go. Was that an automatic time cutoff, Graham? Okay. Don't worry, we're not necessarily going to do all this. I don't know what happened there. It seemed to go to the end. Okay, now we have to be very careful with those isotopic ages, we're certainly dating crystallization, but how does that relate to the deformation? Because they may or may not be coincident in time. Here are some of Calvin's SEM micrographs taken on one of the samples here from the top of the Moine thrust zone at the south end of the Kyle of Tongue, where monocyte grains, the light-colored grains in those SEM photographs, commonly share crystal faces and are intergrown with muscovite and biotite. And certainly the muscovite and biotite are associated with that penetrative shearing. Oh, thank you. Thank you. Yes. Okay. Now, there's two possibilities with just that data. They're certainly growing parallel to the deformation fabrics. So the monocyte and xenotime growth could be coeval with microgrowth. And so they're synchronous with penetrative deformation. Or, to at least play devil's advocate, you could have a pre-existing anisotropy in the rock, and these grains just happen to be growing along planes of weakness. They're basically mimetic mineral growth. And it can be very difficult to tell the difference. That's important because are you dating the timing of deformation, or are you just merely dating later crystallization? It's really fundamental to understanding what's happening in terms of the tectonics. In this case, I think we can make a case that at least that crystallization is close to deformation, because the temperatures of crystallization that we get from the monocyte grains are clearly overlapping with the temperatures that we have from the deformation fabrics. It's not a foolproof piece of evidence, but I think it's making it very likely, at least, that we're broadly synchronously dating deformation, because this is all happening at the same temperature. Not foolproof, but I think it's relatively persuasive there, that these monocyte ages are synchronous with deformation. Okay, now, we got to get the things up to the surface yet. So we have these rocks sitting down at about 550 degrees Celsius, deep in the crust, probably 20, 25 kilometers down. And we've got to get them up to the surface and lay down lower overhead sandstone sediments on the top by lowermost Devonian times. This is where now Ryan's PhD student at Kentucky comes in, because for his PhD in the southern Moine, he was looking at the exhumation history of these rocks. So the cooling history now, bringing those rocks up to the surface by lower Devonian times. Here we have some of Brandon's data from different parts of the Moine thrust sheet, going through the Naver and the Skinsdale thrust sheet there. So we have that data. He has data from amphibole, all argon, and from white mica. They have different closure temperatures. So an argon age from, say, amphibole, that will reflect when the mineral is cooling through about 550 degrees C, whereas the argon data and the experts argue amongst themselves about exactly where that should be. But basically at about 400 degrees, the white micas should be cooling and recording the time that they cool through about 400. So here is Calvin's data in here from the monocytes. And we have to get those rocks to the surface and lay down Enzian sediments by this time here now. Okay, so here are, in terms of just purely temperature, here are the muscovite ages coming through in terms of ages. And the monocyte ages are actually getting younger towards the foreland. So if you look in detail at these monocyte ages, the monocytes are getting younger towards the foreland, and the muscovite ages are actually getting older towards the foreland. That's to be expected for the muscovite ages, because rocks out at the edge of the mountain belt will come up and cool before deeper rocks, deeper in the mountain belt, come up and cool through the same temperature. So that's to be expected. The ones at the edge are older there. Now, let's summarize what we have in terms of ages. The Moine and Ben Hope thrust sheets associated with top to northwestern thrusting, and their age ranges between about 412 and 420 million years. Much, much younger than the ages bracketed on the Moine thrust zone itself. Within the Naver thrust sheet, those are slightly older, going back to about 430 million years. And once again, they have to be exhumed to the surface by Emsian times, when the lower overhead sandstone laid down. All of this is much, much younger than the ages coming out of the Moine thrust zone. So I think we have to rethink about the Moine thrust being the last gasp of motion on this part of the Caledonian mountain belt. Things were clearly still going on in the hot interior of the mountain belt when main ductile motion, at least on the Moine thrust zone, had finished. Now, we do have lots of detailed petrologic data, both in terms of pressures and temperatures. I'm not going to say very much about it, but we know certainly both for the Ben Hope thrust sheet and the Naver thrust sheet that we have a pressure temperature loop deep in the crust up to the Earth's surface. The pressure temperature loop like this. This is all constrained by metamorphic petrology. And then when we get into this part of the paths, we can build in the isotopic dating as well. So the lower parts, we can get the pressures and temperatures, but we're not really sure about the timing, except it's obviously earlier. But when we get up into here, we can now couple the metamorphic petrology with the isotopic dating. So we can be much more confident of the time at which the rocks pass through these parts of the exhumation paths. And of course, we have to get them up to the surface to lay down overhead sandstone sediments on the top. And those are thought to be Emsian in age, so they're in lowermost Devonian times. Now, this is all Brandon Spencer's work at University of Kentucky. Here we have one of these Devonian overhead sandstone basins sitting on top of now the eroded orogenic core of the Himalaya, of the Northern Highlands terrane. So we brought those crystalline rocks right up to the surface, and now we're depositing these overhead sandstone rocks on the top, okay? Those are known to be in Emsian in age, so they range between 408 and about 393 million years. Here, Brandon's produced a very complicated diagram, certainly, temperature versus age, and for the different thrust sheets, the Naver, Skinsdale, Ben Hope, Upper Moine thrust sheet, et cetera, for those different thrust sheets that are different color-coded, we have the times at which they're passing through these temperatures, and therefore, assuming a geothermal gradient in here, the temperatures at which they're coming through these levels in the crust. And they have to get up to here at the surface to form these ORS basins. Now, in this temperature time plot, the steeper the slope, the faster the cooling, and the faster the exhumation rate, okay? Now, the Moine thrust sheet is the only thrust sheet where you start off with a steep curve going up to about 400 degrees, and then to get to the surface, you come to a more gentle curve. So in this last 10, 15 million years, something like that, the rocks are coming up slightly more slowly than they were in the early stages of their uplift in exhumation. That's to be expected numerically. However, these other thrust sheets, it's the other way around. Gentler slopes here at high temperature, and then they have to, their slope for exhumation actually has to increase to bring them up to the surface. That's very unusual that the rate of exhumation is actually increasing towards the later stages of development. Now, you can work out the time averaged exhumation rate. It is time average rather than any moment in time. And you can see here that the exhumation rates are usually in the sort of 1 to about 4 millimeters per year, time average there, okay? Now, those time average rates for the Northern Highlands terranes are actually comparable to present day erosion rates in low latitude, in other words, temperate to subtropical, active mountain belts dominated by fluvial erosion. Now, why did we pick low latitude here? Quite simply, because at that time, we know from PaleoMag that Scotland was about 15 degrees south of the equator. So when these rocks were coming up and eroded, that part of Scotland was actually pretty close to the equator. So these modern day equivalents are quite relevant for what was going on. However, the problem is that those erosion rates should decrease both away from the orogenic core, which they do, and the erosion rate should actually decrease as you have progressive amounts of erosion, because you're starting to get less and less material eroded away. And that's not happening. In the high temperature core of the Northern Highland terrane, there appears to be an acceleration in cooling and exhumation rates from peak to late stage orogenesis. On the basis of that, Brandon Spencer suggested that something additional must be going on. And what he suggested going on was similar to what's been, for example, suggested for the East Greenland calodnides and has been suggested for part of the Himalaya. If erosion is going on at accelerating rates, that suggests there's some other process also acting to take away that overriding material more rapidly. And what Brandon suggested was, it's actually late stage normal faulting, where basically you're tectonically slicing off part of the mountain belt. And hence that's why you have the faster erosion and exhumation rates, is because you're tectonically, by normal faulting, slicing away that overlying material at a much faster rate than fluvial erosion could do. Now, if that does occur, and Graham will know better than I do, such things have been documented for the East Greenland calodnides, where's the evidence for that? Well, you've got to remember this eastern part of Scotland is dominantly blanketed by Devonian sediments. So the evidence for it would be under the Devonian sediments, apart from one location. So I'm going to finish on this one last location. For the very last location, and I promise then I'll finish, Graham. We won't get to the Great Glen tonight. For this last location, I'm going to come down here to the east coast in the Creech Peninsula, here. And here we have what's at least mapped as the Skerbeig thrust again, like this. These are Morar group rocks. These are Glenfinnan group rocks. The lineation here is plunging moderately towards the south and east. And here's a cross-section showing what's going on. But if we look at the crystal fabrics in there, the crystal fabrics now are suggesting a top down to the southeast sense of motion, which is what you would expect if you do have late normal faults slicing through the orogenic core. It's only a tiny little coastal section. Wouldn't want to make too big a deal of it. But at least we have a hint here in the Creech Peninsula of what may be under the Devonian cover on a bigger scale, with this top to the southeast shearing. It's the only location I know of in the Northern Highlands terrane where you can actually demonstrate that. And we can date that as well. So Calvin has looked once again at the Monazite and Xenotime in this contact here. It's associated with tops of the south shearing. He has two groups of ages. One certainly is a Precambrian population with intercept ages about 900 and 540 age there. But there's a very distinct separate population of Scandian age grains coming in at about 420 million years. And that's about right for being a player in that late stage exhumation there. Fits in just about right in terms of ages. So we can add a little bit more to the timing now. We said on the western part, the Monozoic ages are suggesting shearing at about 412 to 420 million years, significantly older than on the Moine thrust zone. In the high temperature Naver thrust sheet, about 417 to 430. But the youngest ages are down here on the Creech Peninsula here now and here at about 420 million years on the east coast there. Okay. So we don't, I think, have time for Great Glen. So let's go to finish off for thoughts for future work. I'd personally like to see lots more isotopic dating needed on the ages of the deformation fabrics, and hence those different kinematic domains, wherever they are. Throughout the Northern Highlands, but now particularly in the southern part, which I haven't mentioned at all, where there really is very, very little in the way of age control on what's going on. And I think that needs campaign style age dating rather than just measuring one or two locations. I think it really needs to be a regional coverage in there. And I think that would give a lot of new thermal insights into the thermal evolution of the Northern Highland terrane. There is obviously a problem unequivocally linking crystallization ages to deformation ages. So we always have to think of ways to integrate the different deformation and isotopic dating studies to try to get more faith in what we're actually dating. Is it deformation? Is it just crystallization in there? And personally, I'd like to see a campaign-style rubidium strontium, muscovite and biotite dating, particularly the muscovite, because most of these thrust sheets are at sort of lower amphibolite facies temperatures, 550 to 600 degrees. And I think a campaign-style rubidium strontium muscovite dating, particularly the biotites would come in at a lower temperature, could give a lot of insights into what is going on there. And then for myself, I'd actually like to finish off looking at the crystal fabrics and the senses of shear in those really, really high temperature rocks in the far east of Sutherland and Cromarty there. Right, I'll stop there. Thank you, Graham.